So the next thing I'd like to turn to now is interpreting the coefficient C sub n in terms of measurements of the energy of our wave associated with our system, of our particle described by some wave function. So it turns out, through a few things, the only results we can get for a measurement of the energy are one of the allowed stationary state energies. Volts we can get are one of the E sub n. So this perhaps is one of the more unusual features of quantum mechanics, right? Because for a classical system, the system can have sort of any arbitrary energy, right? We saw, right, that when we solved for the stationary states, right, the stationary states only have some allowed energies, but it turns out to be more general than that, because no matter whether you're in a stationary state or not, if you go and try to measure the energy of the system, the only thing you can get is one of those stationary state energies. Right, so now you know that if you're in a stationary state, if and let's just say that you're in the state psi n, right, then the expansion coefficient associated with that sort of is 1, right? You're 100% in the stationary state, and everything else is 0. And if you're in a particular stationary state, right, of course you're going to measure the energy associated with that stationary state. So if you measure E, you get that nth stationary state energy that goes like n squared pi squared h bar squared over 2m l squared. But what if you're not, right? If you're not in a stationary state, right? And then the Cn, as we said, tells you how much psi n-ness you have in your wave function. It turns out that the following holds, right? If you're not in a stationary state, right, there's now not just you're not in a state of definite energy. It turns out that you have a probability for measuring different energies, just like with position measurements, we talked about probabilistically. When we talked about those single photon interferometers, we talked about probabilities for being detected in one arm or the other. If not a stationary state, then it turns out that Cn squared equals the probability of measuring the energy being En. Now, this, right, this is a new idea. Right? If it feels like it doesn't sort of obviously or logically follow from what came before, it doesn't, right? In some sense, you can think of this as sort of another principle of quantum theory, and on Monday I'll spend some more time talking about how all the pieces fit together, but this is really a new idea. There are some things we can say to make this a little bit more palatable, I think. Again, I think this connects deeply with the idea of Cn being a measure of the psi n-ness here, right? The bigger your Cn is, sort of the more psi n you are in some particular wave function, and it would maybe be intuitive that you then have a higher probability of measuring the energy being E sub n. There's one other result that I'm just going to mention that helps maybe make this plausible. If I once I erase the board, I'll roll back on over. So one piece of evidence that suggests that C sub n modulus squared acts like a probability comes from the following. So if you perform a calculation based on orthogonality, and I think this is one of the things I will go through in detail in an extra bonus video for today, using gives, right, so the sum on n modulus squared equals 1, right? So this turns out to be right. You know that the total probability of all possible outcomes has to be 1. So this is just like all have to add up to 1. So that's, again, not definitive proof, but it's at least suggestive. There's one more piece of evidence that I'll also mention in terms of consistency after we finish the last part of today's class, and I'll also discuss the mathematical details behind that in a bonus video. So, again, the key takeaway is that, right, so is what I just said earlier, right, that Cn squared is the probability of having measuring energy to be E sub n. Now this has some cool implications, right, because it now gives us the ability to calculate the expectation value of the energy if you're not, well, in any state. So this leads to the expectation value of the energy. So again, if I have an ensemble of identically prepared systems all described by the same wave function, and I go and make energy measurements, the expectation value is the average value I would get from measuring those many identical systems. Well, you know how to calculate that. It's just like any expectation value. I have to add up over all the possibilities, the energy and the probability of getting that energy. And so let me write that as prob. So this is now just like, I think we did an example with like rolling dice where like there are discrete, you get values you can get if you roll a 6-sided die. This is just the same, right? You have discrete values of energy. You need to multiply by the probability of getting that energy and add them all up. But we now know what that energy probability is. It's just the C sub n. And so what we get, and let me roll over because this is also sort of important, right? Turns out our expectation value for the energy is none other than the sum on n of E sub n C sub n squared. And later in the class we'll do a whiteboard exercise where you can practice applying these results. So the last topic I want to talk about today has to do with measurements and operators and eigenspaces. what I'm calling eigen stuff, so eigenfunctions and eigenvalues. We will, again, I think I will take Monday's class to spend some time just tying together some loose ends and everything we've done and learned using the infinite square well. But just a few things. So as I mentioned, I think in a previous class, right, in quantum mechanics, right, observables, so things that you could conceivably measure about a system, are associated with operators. Right. And we've already met several of them, right? We've seen position, and I'm gonna write x hat for, so this is the position operator, so Townsend tends to write sub OP. I think that's a little silly. Certainly, I think the more common notation is a hat. And I'm gonna write, so this arrow is not an equal sign, but it's saying the expression of this operator. And there's some subtle reasons behind that I'm happy to talk to people offline about, or will certainly be discussed in Physics 421. But the position operator, right, is just x. Momentum, right, we learned that, right, this operator is represented as minus IH bar times the spatial derivative, right? And we can build other operators out of any combination we want of position and momentum and constants. So, right, if we have a potential energy, right, that depends on position, well, we're allowed to incorporate the position operator. So the most important new operator we need to talk about today is energy. And here we mean the total energy of the system, which is the sum of kinetic energy and potential energy. The kinetic energy, right, takes the form p squared over momentum squared over 2m plus whatever our potential energy is. V of x, right? And so this I should really think of this as as an operator, my potential energy. And then if I express this, right, then I have, right, minus h bar squared over 2m times the second derivative with respect to position plus my potential energy. Now, as a function of x, right, it has a special name. This is what we call the Hamiltonian operator, and we give it an h hat, so the why this is called the Hamiltonian, so it has to do with a more advanced formulation of classical mechanics. If you go and take advanced classical mechanics, which is, I want to say it's like 311, right, you will learn about another way to do mechanics without invoking Newton's laws. It's called the Lagrangian approach to dynamics. It involves doing calculations with something called a Lagrangian, and it makes a certain class of mechanics problems way easier to solve than they would be from sort of directly applying Newton's laws. Once you know the Lagrangian formulation of mechanics, there's sort of a further sort of up a level, which is to learn this Hamiltonian formulation of mechanics. And I'm not sure if our advanced mechanics course always gets to that. You might have to go and take classical mechanics in graduate school to see this. It's useful for sort of analysis of like, particularly for analysis of like chaotic systems, but that's where it comes from. The energy operator so is called the Hamiltonian. Now, you might have noticed something about this, because I venture to say that you've seen this before. Think about it, right? This is basically the left-hand side of the time-independent Schrodinger equation sort of written as an operator, right? So this is right? Other than I have to act this on a wave function, that's the left-hand side, right? So this leads us to something really cool. I now need to introduce the idea of eigenvalue and eigenfunction for an operator. So let me erase the board and then I'll do that. So we can define an eigenvalue, an eigenfunction, in the following way. So for an operator, which I'm going to call a hat, right? If for some particular function, and I'm going to write the function as f of x just to be completely general, the following holds, that if my operator acts on my function, if that gives me the function back multiplied by a constant, where then f of x is an eigenfunction of my operator A of A, whoops, with eigenvalue little a. So just if you're curious, eigen comes from the German, and it means self. And those of you who have taken linear algebra will probably have seen eigenvectors and eigenvalues before. Think of this as a generalization of eigenvectors. And if you haven't taken linear algebra, this is your first exposure, and it'll probably come up again in courses like math methods. So what's a good example of this? The absolute best example has to do with the time-independent Schrodinger equation and what it means. So let me, I think I can fit that in here. So, right, so the time-independent Schrodinger equation, we know, right, that's minus h bar squared over 2m d squared dx squared plus my potential energy acting on psi. So I'll label it as psi sub n, because the answers are the solutions are the stationary states equals E n psi n of x. But as we just said, right, this is none other than my Hamiltonian operator. So I can rewrite this as Hamiltonian acting on stationary state psi sub n equals E n of x. So what this shows us then is the following. So stationary states they are eigenfunctions of the Hamiltonian with eigenvalue E sub n. E sub n. Right? And so this sort of leads to other terminology you might sometimes see for stationary states and that I will use. And so we'll also end up calling them, rather the stationary states, so if I can just roll over the top here. So stationary states psi and x, they're called energy eigenfunctions because the Hamiltonian is the energy operator. And that's the language that Townsend uses. I will often call them, and I think you'll find more sort of in 421, you also use the language or energy eigen states. So, and I have a little surprise for you at the end of today's class about energy eigenstates. So stay tuned. So I want to give you two more examples of eigenfunctions or eigenstates and operators. So the next one I want to mention is position. X hat. So operator. So what are the eigenfunctions of position? Well, if I just draw some arbitrary wave function, I think you can convince yourself that that's not going to be an eigenfunction. So, for instance, if I have some arbitrary wave function, and let's just say it has, something like that. If I take this wave function and I multiply it by x, that's going to end up changing the shape of the wave function, right? The bigger the value of x, the bigger the value I'm going to multiply, like that psi of x, that psi at that value of x phi. So I'm not going to get the same function back, but multiplied by a constant if I have just some arbitrary shape here. So let me cross that out. So that is not an eigenfunction. It turns out the only thing that is an eigenfunction of position is something we talked about briefly before, and it's the idea of this really, really sharp spike. So what is it? A position eigenfunction, right, at some position x naught is a spike. So imagine that this wave function is zero everywhere, right, except in sort of an infinitesimal window around some value x naught, right? Why is this a position eigenfunction, right? If this is zero it's basically zero everywhere except x naught. Well, if it's zero everywhere and I multiply this function by x, over most of the function's domain, I'm multiplying x by 0. There's sort of only one place I'm not, and that's x naught. But if I'm sort of multiplying x naught by the spike by x naught, I'm just going to get x naught times my spike back, right? And so this turns out to be a position with eigenvalue x naught. Now, if it seems like I'm sort of pulling wool over your eyes with being hand-wavy about some stuff, I totally am. So this position eigenfunction is weird, right? Because I said it's 0 everywhere except at one point, and if you think that this is the sort of thing that gives mathematicians nervousness, you're absolutely right. This is a mathematical object that does tend to give careful mathematicians conniptions. This is called a Dirac delta function. And I'm not going to say more about it for now, except to say that there are ways to sort of put this on more or less a firm footing, but you should really just think of this as a very sharp, very narrow spike. So that's position. The other case that I want to just mention, and the other case for which we can find an eigenfunction is momentum. So if I have the momentum operator, right? It turns out that the eigenfunctions of momentum are none other than our plane wave functions we were talking about in chapter 2. So if I just stick a constant in front, right, our plane waves is a momentum eigenfunction. So my suggestion at this point would be pause the video and see if you can try to show this for yourself by applying the momentum operator. So pause, think about it, but then I'll explain how I thought about it. Okay. So you've thought about this. Let's see how we can apply the momentum operator, right? Px acting on this wave function, right, is IH minus IH bar partial, one partial x acting on A e to the ikx. Right. If I differentiate this with respect to x, right, the only x-dependent thing is that e to the ikx. I pull down a factor of ik by the chain rule. And so it's minus I h bar times ik times by wave ikx minus omega t. So you see, we get the function back, which is the definition of being an eigenfunction. And the eigenvalue is evidently this combination of stuff, minus IH times IK. But, right, minus I times I is 1, and this is h bar k times psi of xt. But h bar k is just the momentum of this wave function, right? So that's just the momentum, right, according to de Broglie, psi of xt. So that is, in fact, this plane wave state is, in fact, a momentum eigenfunction. So last thing I'll mention for today is the following. So remember how we learned how to find expectation values of like momentum and position? Well, the same thing applies for any operator. For any operator A, it turns out that the expectation value associated with measuring the observable associated with this turns out to always be writable in the following form. The idea is that we sandwich the operator between my wave function and integrate the whole thing over all of space. Oops, there's a little bit of, that's better. And integrate the whole thing over all of space. What I'll show in the bonus video is in fact that the expectation value of the energy, or if I write it as an operator, it's the expectation value of the Hamiltonian, right? So if I stick the Hamiltonian in here into this expression and calculate it, that turns out will show to be exactly equal to Cn squared E of n, and summed over n, and this will be evidence that we are in fact correctly interpreting Cn modulo squared as the probability of getting energy E sub n. So we'll wrap up today with a whiteboard exercise where you'll go and calculate some things about energy for a wave function in a superposition state for an infinite square well. And then the very last thing that I want to share with everybody is actually a song about energy eigenstates. This was actually recorded at an APS March meeting several years ago. I'm pretty sure I was in the room, so perhaps I think I'm probably sort of in the background on that recording. It's a fun little song. If we were together, I might be open to performing it for you. I may be convinced, but I hope you have fun with it and that it's a fun way to go into the weekend. So I'll make a bonus video going over the solution to the whiteboard exercise and some of the mathematical results that I haven't derived in detail. But I hope you have fun with the energy eigenstate song. And yeah, I'll see you on Monday. Let me know if you have questions.